Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So, in the previous lecture we said that we will start now the analysis of higher order nonlinear systems. One of the prominent examples where you would find this in a physical example is the reactor dynamics. We will take this particular situation in the next 3 lectures in fact, but before we go about analyzing a reactor system, which is an incredibly complex system, we first must equip ourselves with a basic understanding of higher order nonlinear systems, so that we can perhaps use those concepts in studying relatively complex problems. So, let us start our analysis. What we have here in front of us is a second order system. So, I have a system of 2 equations, dx 1 by dt is equal to minus x 1 and dx 2 by dt is equal to x 1 squared plus x 2. Okay. We will try to analyze this system and see how what can we learn from the analysis of this system. So, not every system of equations which is nonlinear can be solved easily by sequentially solving individual equations, even if they are coupled, and therefore, linearization is something which we generally resort to for solving such systems. But one question which arises is that can we always do linearization and analyze the system in linear domain and try to make conclusion about non-linear domain? Will it always be possible? Or are there some situations where we can get in fact misleading results? This particular example and the next one will give us very good examples of when we can actually rely upon linearization and when we should not. So, let us first try to solve this problem using our usual method, if at all it is possible to do so. So, the first equation has only x 1. So, I can write dx 1 by dt is equal to minus x 1, from where I can write x 1 is equal to c 1 e to the power minus t. So, solution of first equation was not very difficult, and now I will do this dx 2 by dt is equal to x 1 squared is c 1 squared e to the power minus 2 t plus x 2 plus x 2, and this particular equation is not very difficult to be solved. What I can do is I can write here dx 2 by dt minus x is equal to c 1 e to the power minus 2 t. I can solve this equation using the method of integrating factor. It has to be x 2. So, I can multiply both the sides by e to the power minus t. So, e to the power minus t dx 2 by dt minus e to the power minus t x 2 is equal to c 1 e to the power minus 3 t, from where I can write d by dt of e to the power t minus t x 2 is equal to c 1 e to the power minus 3 t, and now I will do an integration. So, I can write this as e to the power minus t x 2 is equal to minus C 1 upon 3 e to the power minus 3 t plus another constant C 2, from where I can write the expression for x 2 as C minus C 1 upon 3 e to the power minus 2 t plus C 2 e to the power t. So, I have equation 1 and I have equation 2. Fine. So, now for this particular example, it was possible to solve this equation easily, and we explicitly got the answers for x 1 and x 2. So, let me write down the expressions. So, let me write down both the equation as well as the expressions. So, the equation is this dx1 dx1 by dt is equal to minus x1 dx2 by dt is equal to x1 squared plus plus x2, and my solutions were x1 is equal to C1 e to the power minus t and x2 was minus C1 by 3 e to the power minus 2 t plus C2 e to the power t. These were the solutions. Now, can I develop the phase portrait of this system using these solutions? Should be fairly straightforward. In the phase portrait, what I should have is on one axis I should have x 1, on the other axis I should have x 2. Okay. How can I know x 1, the curves on x 1 and x 2? I have the solutions. So, I basically have two methods. First method is pretty straightforward. From here I can write dx 2 by dx 1 is equal to x 1 squared plus x 2 upon minus x 1. I will solve this equation, again not very difficult equation to be solved, and then I will get the solution for x 2 in terms of x 1. From that I can draw different curves. There is always a possibility. There is another simpler solution. I have x 1 in terms of t, I have x 2 in terms of t. So, therefore, I can make a parametric plot to so as to get x 2 and x 1. Okay. So, let me adopt the second approach here. I encourage you to solve dx 2 by dx 1 is equal to x 1 squared plus x 2 upon minus x 1 and plot the equation. You should get the same answer. So, let us draw the parametric plot to get the equations, to get the curves. So, I have so the way I would draw a parametric plot is this, very simple, C 1 e to the power minus t and this is comma minus C 1 upon 3 e to the power minus 2 t plus C 2 e to the power t. Okay. So, now the plot is in front of you, and what I can do is I can increase the parameter t from minus 100 to 100. Okay. the plot is in front of you, one curve is in front of you. So, let me draw this curve, and this curve would be this. Okay. Let me change the values of different parameters so as to get different curves. Let me change C1, make it negative, and let us see what happens. You get this curve. Let me make another change and let us see what happens. This is what happens. Okay. So, I get this curve, I get this curve, I get this curve, I get this curve, and so on. Okay. So, so this is fine. This is the exact have we punched in? Let us cross check. E to the power C1 e to the power minus t minus C1 by 3 e to the power minus 2t plus C2 e to the power t. So, these are the various plots that I must get, various curves that I must get. So, let me draw various curves from what I learned from the calculator. I should get these curves. Okay. And then as you would see from the solutions, x1 has e to the power minus t. So, therefore, it should have a convergent behavior along the x axis. So, therefore, and then x2 has e to the power t. So, it should have a divergent behavior. So, in our previous terms it should have a saddle like behavior. So, I can draw the arrows like this. It is not very difficult to see that this is how the phase portrait would look like. So, this is a saddle like behavior, right. And now, this phase portrait was obtained without by explicitly solving the nonlinear equation. Let me do one thing, let me linearize this equation. Okay. So, I know that 0 0 is a solution, is an equilibrium solution to this system of equations. So, therefore, in close proximity of 0 0, in close proximity of 0 0, my x1 squared will have a very small value, right. So, if x minus x1 minus x1 equilibrium is a small quantity, x1 minus x1 equilibrium squared will be an even smaller quantity. So, therefore, one way of linearization is, so I have linearized model here. I have the linearized model here, and I can write the linearized model as this: dx1 upon dt is equal to minus x1. This equation was already linear. So, nothing problematic here. The problem is that the other equation was non-linear. So, I make this other equation linear by simply setting x1 squared to 0. And why am I doing this? I can do this only because 0 0 is my equilibrium solution, and in close proximity of 0 0, x1 minus x1 equilibrium squared will be a negligible quantity. So, if I write this as simply x2 by making x1 0, I now have a linear model. So, I can write this as d by dt of x1 x2 is equal to minus 1 0 0 1 x1 x2, and the solution is very straightforward. I know that the solution is going to be x1 x2 is equal to C1 e to the power minus t 1 0 plus C2 e to the power t 0 1. We have seen this over and again. Okay. So, for the linearized case, how would the phase portrait look like? Well, the phase portrait is very simple. this is x 1, this is x 2, this would be the divergent axis, this would be the convergent axis, and beyond this you will have the saddle solution. Please refer to our previous lectures to see how we got this solution or this phase portrait. And what kind of phase portrait is this? This is a saddle phase portrait. So, therefore, about very close to 0 0, both the phase portraits give qualitatively similar behavior. At least qualitatively the behavior is very similar. Both of them show saddle solutions. Let us now take another example. Okay. Now, I have another case where you have dx 1 by dt is equal to x 1 squared and dx 2 by dt is equal to minus x 2. Okay. So, dx 1 by dt is equal to x 1 squared and dx 2 by dt is equal to minus x 2. The solution would be x 1 is equal to 1 upon c 1 minus t and x 2 is equal to c 2 e to the power minus t. These are very simple equations. The solutions are in front of you. So, now can I develop and now what would happen to the linearized form? The linearized form would be dx 1 by dt is equal to 0 and dx 2 by dt is equal to minus x 2. So, my linearized equation would be d by dt of 0 0 0 minus 1 sorry d by dt of x 1 x 2 is equal to 0 0 0 minus 1 x 1 x 2, where my first lambda is 0 important and the second lambda is minus 1. Let us now compare the two the behaviors of these two cases. So, my first non-linear dynamical solution is this: x 1 is equal to 1 upon c 1 minus t and x 2 is equal to c 2 e to the power minus t. Let me draw this. So, I will draw the parametric equation 1 upon c 1 minus t c 2 e to the power minus t. Okay. Let me increase this from minus 100 to 100. Okay. See the plot which we get here is the decaying behavior asymptotically reaches to 1, and let me change this. Well, qualitatively nothing changes, now it gets inverted. Okay. So, let me draw this phase portrait here. The phase portrait would look like this. This is x 1, this is x 2. So, the phase portrait is this. Now, this is strange because we have never come across any situation till now for the analysis of linear systems, where the phase portrait would look like this. This is very different. How is this different? Let us see what are the different phase portraits which we came across. Well, we came across this saddle x1, x2, saddle. We came across this source x1, x2 depending upon relative magnitudes of lambda 1 and lambda 2, the orientation may change. So, this is saddle, this is source. Then you have sink x1, x2. Sink. All three for real eigenvalues. Then we had center x1, x2, center. We had spiral source x1, x2, spiral source, and finally spiral sink. x1, x2, spiral sink, and compare it against this particular phase portrait which we got in this study, x1, x2. There is no way that you can approximate this phase portrait to any one of the 6 phase portraits that you studied previously, which means that close to this 0 0 solution we are concerned about, we anyway know that you can make approximation only close to 0 0, the equilibrium solution. So, but even close to 0 0 the equilibrium solution, the behavior is very different. And why does this happen? This happened quite simply because in this particular case one of your eigenvalues was 0. So, we have Hartmann-Grobman theorem which will give us an idea about this. So, according to the Hartmann-Grobman theorem, the orbit structure. So, let us first try to understand what is the meaning of orbit structure. Orbit means evolution, right, in a very general sense. So, in a discrete system, for example, if you start with a point and the dynamical system is a system in which the variable changes with time. So, that particular point would keep on evolving in time. So, that would result in an orbit. An orbit structure means the arrangement of different phase lines in a particular region, right. So, the orbit structure of a dynamical system in the neighborhood of a hyperbolic equilibrium point. So, we know the meaning of equilibrium point, but now we have a new term, hyperbolic equilibrium point. We will come to this definition a little later. So, in the neighborhood of a special type of equilibrium point known as hyperbolic equilibrium point is topologically equivalent. Topologically equivalent means the geometrical features of the arrangement of the phase lines. Okay. So, it would be topologically equivalent to the orbit structure of the linearized model, the linearized system. Okay. So, what is the meaning of this? So, what it means is that if you take a non-linear system and imagine that you have some way to determine its complete phase portrait, then you would be drawing that phase portrait. So, that phase portrait will be a collection of phase lines, and since it is a collection of phase lines, there would be arrangement of these phase lines around the equilibrium point, right. And then what you would do, you would linearize the system and again determine the topological features, which means you will determine the orbit structure, which means you will determine the arrangement of phase lines close to the equilibrium point near the for a linearized system. Now, if the equilibrium point is hyperbolic, then according to Hartmann-Grobman theorem, the topological features would be equivalent, which means the nature, the dynamical nature would be similar. Now, the only thing which is left is to understand what is the meaning of hyperbolic here. Hyperbolic means no eigenvalue will be 0. This is important. If there is even one eigenvalue which is 0, or no eigenvalue will be 0, or will have 0 as the real part. Well, the eigenvalues can be either complex or real. So, in cases where the eigenvalues are all real, no eigenvalue should be 0, and if the eigenvalues are complex, then the real part of none of the eigenvalues can be 0, and if that is the case, then the equilibrium point is called a hyperbolic equilibrium point. So, how would you then assess whether it would be possible for you to linearize the system and have a guarantee that the linearized system will indeed have the same features as the non-linear system? Well, you will determine the equilibrium point, you will determine the eigenvalues, and if with the help of the eigenvalues, if none of the eigenvalues are 0 or 0 as the real part, then you will declare that those equilibrium points as hyperbolic, and if the system has hyperbolic equilibrium points, then you can say, then you can assure yourself that you in fact have a system where linearization would work. Now, in the previous examples, you could trivially do linearization by setting the non-linear part on the right hand side as 0, and that was possible because you had the equilibrium points as 0 or 0 0 and so on, right. But what will happen when you do not have the equilibrium point as 0 0 or equilibrium solution at origin? Then you will have to do a proper Taylor series expansion for linearization. Let us see that. I have dx1 by dt is equal to x1 squared minus x2 squared minus 1 and dx2 by dt is equal to 2x2. So, let me call this as f1 and let me call this as f2. What would be the equilibrium solution? Equilibrium solution would be obtained by setting up f1 is equal to 0 and f2 is equal to 0, right. So, I can determine the equilibrium point as x1 squared minus x2 squared minus 1 is equal to 0 and 2x2 is equal to 0, from where I get x2 is equal to 0, fine, and therefore, x1 squared minus 1 is equal to 0, which means x1 is equal to plus or minus 1. So, what would be x1 equilibrium, x2 equilibrium? There would be 2 x1 equilibrium, x2 equilibrium minus 1 0 and 1 0. Both of them are equilibrium solutions and they are not 0 0. In this case, you cannot simply do this linearization trivially by setting up the square terms to 0, and therefore, we would determine the linearized model by following the proper Taylor series expansion. So, let me see if we can do that. So, x 1 squared minus x 2 squared minus 1. So, d x 1 by dt is x 1 squared minus x 2 squared minus 1, and dx 2 by dt is equal to 2 x 2. Okay. So, now what I need to do, and I had x 1 equilibrium, x 2 equilibrium is minus 1 0 and 1 0. So, let me do one thing, let me assign this as f 1 and f 2. I will determine the Jacobian. So, del f 1 by del x 1 would be equal to 2 x 1, del f 2 by del x del f 1 by del x 2, del f 1 by del x 2 is equal to minus 2 x 2, del f 1 by del x 2, sorry, del f 2 by del x 1, del f 2 by del x 1 is 0, and del f 2 by del x 2 is 2. So, therefore, my Jacobian matrix is, the general Jacobian is 2 x 1 minus 2 x 2, 0 and 2. Okay. So, in order to get the idea about the solutions, what I will do is I will determine this Jacobian at minus 1 0, and this is going to be minus 2 0 0 2, which have the eigenvalues minus 2 and 2. For the second Jacobian at 1 0, this is going to be equal to 2 0 0 2, which means the eigenvalues are repeated 2 and 2. So, from these eigenvalues I can have an idea about the nature of the solutions, the nature of the linearized solutions. Now, would linearization work in this case? Yes, linearization would work, because none of the eigenvalues are 0. So, I can expect the linearization to work. And finally, can I get an idea about the phase portrait? Well, I can. So, to develop the phase portrait, what I would do is I know that my equilibrium solutions are x 1 equilibrium and x 2 equilibrium are minus 1 0 and 1 0. For this, the eigenvalues were minus 2 and 2. For this, the eigenvalues were 2 and 2. So, let me draw x 1 x 2 here, x 1 x 2. Now, my first equilibrium solution is minus 1 0. So, this is minus 1 0. My second equilibrium solution is 1 0. So, this is 1 0. Now, minus 1 0 is associated with two eigenvalues, one of which is positive, the other one is negative. So, it should have a saddle behavior about that point, and 1 0 is associated with both positive eigenvalues, it should have a source behavior about that point. So, how can I draw phase lines which would both conform to this particular situation? Let me see, can I draw this? So, let me do this. what if I drew curves like this. Now, what is left? What is left is to draw the arrows. So, since this is a source, this would go up, this would go up, and from here, since it is a saddle, it should go like this, right. So, since this 1 0 is a source, you should have corresponding arrow here, should have corresponding arrow here, and following the arrows of the leftmost portion, you should have the arrow here. Okay. And again, you will see here that this is a saddle, all the arrows conform to a saddle behavior, and this is a source, all the arrows conform to the source behavior. So, this is how we will handle higher order nonlinear dynamics. What you do is, the first thing which you establish is the equilibrium solutions. The equilibrium solutions are arrived by setting up the individual equations to 0. Now, in most cases, since it is not possible to use the nonlinear model directly, you would like to linearize the system. How can you be confident that your linearized behavior is similar to the behavior of nonlinear system? Well, what you do is, you would establish whether the equilibrium solutions are hyperbolic or not. So, following the Hartmann-Grobman theorem, if the solution, if the equilibrium points are hyperbolic, which means that none of your eigenvalues are 0, then you can in fact use linearized phase portraits, and the orbits would be similar to those of a nonlinear system. The method which we developed today will be used from tomorrow onwards to analyze the system of reactors in case of transient operation of reactors. Till then, goodbye.